Hello, and in this episode, we're going to be discussing what our strategy is for the queries and how we're going to ensure that we're only getting the entities, or rather the components, for the entities that we want to query. So I've got an example here on our whiteboard of like what we might be looking at. This is very similar to what we have in the integration test. I just added one extra component type to sort of like show off how this can scale. So let's say we have player one and enemy two here. So at the far ends of each of our sort of like vector of vectors, they have all three components. They have location, sizes, and health. Everything else is missing something. So if I want to query for something that has all of them, well, how do I do that? Well, one potential answer here is for me to recreate our hash map, but then add in information like, do you have this or not? So it would be basically a map of the components that each entity has. So if I just take this entire thing and I copy you down, all the locations you get copied down too. And then this would essentially become a 1, 1, 1, 1. You're a 1, you're a 1, and you're a 0. Because otherwise we have like basically nuns and sums there. You're a 0, you're a 1, you're a 1, 1, 1, and 1. So just looking at this, I can easily tell that I want player 1 and enemy 2 here. So if I'm querying for this, I can see that as a human. But how am I gonna have like a computer program look through this? And if this is really a hash map of vectors looking through this, that's gonna be, not all that awesome either. But there is a way to represent this into a single number that's gonna actually make it a lot easier for us. So what I really want to do is represent each of these just in a single number up here for each entity. So how are we gonna do this? Well, I want, like, it's not gonna be something like 1, 0, 0, 1. Like that doesn't make sense because, well, this has locations. I don't have that kind of information here. But what I can do is we can use a little bit of binary math to sort of help us out here. So let's say we have locations and we're going to represent that by the number 0b. In a lot of languages, writing a number as like 0b first allows us to now represent whatever we're writing like as the actual binary, and it will convert it into decimal for internal use. So 1, 2, 3, 4, 5, 6, 7, 8. Now, oftentimes, when we talk about binaries, we talk about like 8-bit numbers, but we can go much higher than that. So this is an 8-bit. It basically is just like a U8. We have 7 zeros, and then the final one is set over here. So we can just say this represents locations. Well, what if I do the same thing for sizes, but instead of this 1 over here, we go 1 left, and then we do another one, and you are 1 more to the left. And then if we continue to add component types in, we just continue to add another 1 over. Now, a big thing to note here is that I can't have another 1 in here. Like 2 1s in one of these numbers is actually going to break the entire system. It has to be exactly like this. Now, if you're familiar with binary, the way that this works is each digit here gets assigned is like based on power of 2. So let's move this over up here. We're gonna go take a look at it in a little bit more detail. So over here we have the ones place. So that probably makes sense. It's just the number 1. Let's also make you a little Here, we'll make you orange. Then over here, we have the 2's place. And then 4. And then 8. So it's really power of 2's. So it's 2 to the power of, what is it? 2 to the power of 1 or 2 to the power of 0? That's, I think it's like, yeah, 2 to the power of 1, to the power of 2, to the power of 3, to the power of 4. And then that's giving you this number here. And then as we continue going on, that's 256 at the very end here. Now, that's just a U8. If we then move on to, I think we can go up to like U128, maybe even a U126. Oh, it's 2 to the power of 0. Yes. For this one right here, and then 2 to the power of 1, 2 to the power of 2, to the power of 3, and then so on. What this means is that however many digits we have here is how many components that we can have. So this is a U8. We can, I believe, go all the way up to a U128, which would allow us to have 128 components in our system, which I think is more than enough. We can probably stay with U32s to begin with, and then if somebody requests it, we can then move up to a U128. Now, of course, this is going to be all based upon whatever simulations you're creating with this this ECS library. If you're just doing this for practice and you're not actually going to build anything with it, it doesn't really matter. But if you are going to build something, then I would keep in mind, like, how many components are you going to need here? It's like, maybe you can have like a configuration option to like choose the upper limit, or basically set what kind of number this is going to be. Okay, so if we know that this is going to work this way, then what we can do here is now create this number based upon the binary math here. So if we have a location and a size and a health, we combine all of these together, which would be a it would be a 1, 1, 1, because we have 1, 1, 1 here. This one would be a 1, 1, 0. So now we also have to like consider here, locations is this far right one, and health is this far left one. So it actually would be the 0 here, just 1, 1 there. Oh, I'm doing this wrong. This is here, here, here. Okay, for you, we have no location, but we do have health. So you have 1 there and a 0 there. And then finally over here, we have everything again. So you're back to 1, 1, 1. Okay, now if we just convert this over into decimal, what is that? So this is gonna be 1 plus 2, so that's 3, plus 4, so that's gonna be 7. So this number gets stored in here as a 7. You are a 1 plus 2, so that's just 3. You're a 0 plus a, well, it's not a 1, it's a 2 plus a 4, so that's a 6. And then you're 7 again. So here we can now see, okay, give me everything that has a location, a size, and a health. I could compare this locations. Hey, do you have this? Maybe we can even figure out, hey, I want, for you, do you have basically these positions here? Now there's some math that most languages allow us to do called the bitwise operators that allow us to sort of like very easily check, hey, do you have a 1 in this position? Do you have a 1 in this position? Or in this position? Let's go and experiment around with this a little bit inside of here. So In our main we're going to be in the playgrounds. So let's see. Let's our, maybe we'll call it like the mask, equal to 0b 2 3 4 5 6 7 8. So here's like this number 1. So let's actually call this like the location mask. Let's do like maybe a size mask. And you're going to be exactly the same, except you're like that. And then we're going to have like our entity. So let's say our entity we have 2 entities, one with both of these and one with only one of these. So we're going to have maybe like player, and you're going to have both. So that means you're that. And if we have maybe an enemy that for some reason only has a location, let's say, or I guess it wouldn't be an enemy. If it just has a location and like maybe no size, maybe that's just like a static item behind the scenes. So let's just do like, a tree. And you're gonna be, so if you're a location and no size, you look like that. So if we're looping through all of our entities and we want to find something that has both of these, we have to like determine what we're looking for and if it has it. Well, let's see. If we do a debug, we can start doing some math in here to sort of like figure out what exactly we're looking at. Let's do our location mask and our player. Now notice I'm just doing a single ampersand here as opposed to and. So and will give us a Boolean out, but a single and is going to give us just a number out, which is the number of shared ones here. So we get this location mask and player. So we can see, oh, they share this one here. So that means it does have it. Let's take a look at, let's see. The location mask and tree is going to have the same one here. So let's do a size mask and tree. So we're going to have a size mask and tree. And if we look at this here, so size mask and tree is 0. So size mask is, okay, so he's 0, 0, 1, 0, and this is 0, 0, 1 at the very end. So it's showing that none of the ones line up. And so there's nothing in common, which means the tree does not have a size. That's what we can get from here. However, the player had a 1, therefore it does have a size. Or sorry, it does have a location. It also happens to have a size. So how are we going to use this to our advantage? Well, if we have the original numbers for each of these locations, or each of these component types, so you would be locations, you would be sizes, then for each of the players or each of the entities, we can, as we're looping through them to determine, hey, should we add you into the results for the query? Then we can, what we can do is basically ask, okay, do you have this thing? If you do, let's go ahead and add a reference to you into the resulting, vector. If you don't, then we don't need to worry about you whatsoever. We'll just skip you. Okay, I mean, that seems perfectly fine. So how are we going to store this away? I'm thinking we're going to have a hash map of the type IDs to store each of the component types. That's very similar to what we have right now, but then the value will be one of these. So let's go and maybe start building this out. So in entities, we're gonna have to have we have queries here. We're gonna have to have, or components here. We're gonna have to have the, like, it's not the map itself. So the map is gonna be the number. So I think this is gonna be the mask. Although I keep on getting like the terms confused back and forth. So if I do this backwards, I'm so sorry. Let's do the bit. We'll call this like the bit masks. So bit mask is going to be a hash map. Now inside we're going to have a type ID, but then for the value we're going to do just a U32. So as I mentioned before, we're going to, this is limiting us to have only 32 components in our system. But for this example, I think that's going to be fine. If we need to take up more memory for this, then we can get up to like 128 or potentially even larger if we get really creative with our number types. Okay, so, and this isn't going to limit the number of entities that we can have, just the number of components that a single entity can have. Okay, so we have Bitmask. That's great. If we want to like add something in, like when is that going to be added in? Well, that's going to be added in when we register a component. So let's come down and we're going to have to update our tests here, sort of like to take a look at this. So when we register an entity, we do this register component. Okay, so we have this health here. We would now assume that because it's the first thing that we're registering, that now we're gonna get a 1 into the bitmask for that. Well, what is that gonna look like? Let's we can grab this out of here. Now I wonder if, let's actually create a second test for this. So when we're registering an entity, so maybe this is a bitmask updated when registering entities. That way, this could just remain nice and simple, and then we can have just maybe a slightly more complicated test. Also, we don't have to like just make sure that we're testing, you know, that we got this component out. I don't really care about that. We're caring about the bitmask here. So, and I'm calling it, yeah, I'm calling it bitmask. So we have our entities. That's fine. We register component health. That's fine also. We get our type ID of this, so we can get this out. But instead of the components, we're going to get the bitmask. I'm going to get type ID, unwrap here. So this is going to be a reference to a U32, which is going to be fine. So we actually expect that this, a dereferenced health component, and so this is not really health component. This is going to be more like health mask. Is going to be 1. Now, if I do the same thing again, so if I do another one, so we'll do entities, register, component. We have another one down here, right? Yeah, we have speed. So if we register speed as a component, our type ID of speed, so we can just shadow this. You're going to be speed. If I do this, then we can just shadow these. They'll be fine. We'll do our mask is entities. Bitmask get this type ID. Okay, that's fine. Then assert equal. Okay, so this mask should now be 2. because each one is going to have a unique with only one bit set, and the other ones are not set. And if I do another register component, then we expect it to have maybe, one more. Okay. So if we run this test, we should get some failures because there's nothing in here. So we're going to get probably an error on that none here. Yep, we try to unwrap on a none. That's fine. So if we come back up to here, how are we actually going to do this? So when we register this component, we shouldn't just be self components insert. That's fine. We have this type of ID. Well, first off, we needed this type ID twice. So let's extract this out. Let our type ID is going to be equal to u. And then we can just do this type ID. Now, I don't know if this implements copy or clone. We're going to eventually run into trouble when we try to use it the next time because we've just given ownership of this over. Now, we can go take a look at it, and it derives copy and clone. So we can basically just use it like it's in any other language that we don't care about. It's going to auto clone for us. So I can just use it again. Now I just have to keep in mind that it's not the same one that I'm using, but a clone of it behind the scenes. And that's going to be fine. Now we know we're going to want to insert into Bitmask with this type ID. That's going to be fine. The question is, what are we going to be inserting? Well, it's going to be that binary number, right? Where it's going to be like 1, 2, 4. So how do we know what number to actually set it to? Well, if we think about it, let's come back to our whiteboard. If we're coming down like these are like 1, 2, 4. It's always powers of 2 that's increasing. So we could do some try to figure out the last one that was updated and maybe do a clever bit shift. I was actually thinking about this when I was planning this episode out. But now that I'm thinking about it, there might be just an easier way. What if we take a look at how many things are in the hash map already? So let's say we've already added in locations and sizes. So we have a hash map of the length of 2. Now, I want to make it a length of 3. So I want to take 2. Well, would that be 2 to the power of 1 or 2 to the power of 3? Let's actually just open up our calculator and take a look. If I do, can you do powers of here? Oh, you know what? Is it going to be easier? We'll just do this in Rust here. So if I want to say 2, and let's just make sure this is a U32. Then I can do pow of, let's say 3. And let's debug this. Smash types, expected nothing. Oh, I think we have to pow I. Oh, no method named powi. We have to go find in the documentation what our power looks like. So let's go into a U32. I don't want that one. One of the other U32s. How about this primitive type here? And we want to go find a power. So here's pow. Okay, so we have the pow expression, which is the U32, and then it returns this. So it raises itself to the power of expression. Okay, so look, 2 u32.pow5. Okay. So that works. 2 u32 pow3. I thought that would work out. Let's just double check. Let's put this into a variable here. So let's do like our mask. It's gonna be equal to this. So we have 2 a u32. I'm gonna do a pow3, and then I want to debug out this mask. Okay, so that gives me 8. So if we come back here and look, so 8 is this one right here. And I wanted 1, 2, 3. I wanted this one. So we have to make sure we do it -1. So it's the length -1. Or maybe it's the length that it's existing right now, right? So if we want to add in health now, we already have locations and sizes in. The length is 2. We're gonna come back to here. I'm gonna do pow2. And that gives us a 4, which if we look here is this third one. So that's perfect. So what we can do is we can just do a power. So 2 to the power of the length of the hash map. And that gives us the appropriate binary number that we should be inserting into it. So that seems perfectly fine. Let's come back into here and we will, okay, so we're gonna insert into here, that's fine. Let's also figure out what our Bitmask should be. So that Bitmask. We remember there's gonna be 2 to the power of, so let's see, 2, that pow, and then we're gonna have to be at the length of bitmask. So self.bitmask.length. That's gonna give us, let's see, ambiguous number type. We're gonna figure this out. It should understand what it is because it's this U32. So then bitmask, we're gonna insert in after this. So we're gonna do self.bitmask, insert. Our key is gonna be this type ID, and then the value is gonna be the bit mask. And suddenly it knows that this is a U32 and then should be happy. Oh, but it doesn't know exactly what this is. So this is 2 U32. We get to a power, and then you are the wrong type also. So a length is always a U size as opposed to a U32. So we just need to convert this into a U32, which has a possibility of losing some data, but for the sizes, the lengths that we're gonna have, it's never really gonna cause a problem. So we're just gonna do an as U32. So we'll cast that down explicitly, and then that should make us happy. So now our bitmask now comes in here, and we should have exactly what we're expecting. Let's come back down and run this test. And it passes. So we are running the bitmask updated. So that means that we're getting exactly what we're expecting here each time that we register a new component. All right, perfect. So that's gonna be like the first part of this, right? Because we now have essentially the components we need to start tracking what these are gonna be. So in the next episode, that's what we're gonna do. We're gonna create the actual map, which is going to be, hey, entity 1, you have, all of these. Entity 2, you have, all of these, and so on. I'm looking forward to that, and I will see you in that episode. Bye.